This is Unit 5, Lesson 3, Part 2, the first derivative test. So we talked about looking at a graph in the last video and how to understand the ideas that we have intervals of increasing and decreasing, and how moving from one interval to the other can help us find where there is a relative min or max. So now what we're going to do is we're going to figure out a way to find the values of x on the graph where it is increasing or decreasing or constant. So we want to start with the idea that we have a continuous function, and we can understand probably a little better in these beginning stages that the derivative is only going to change signs at a critical value. But if f is discontinuous, then the derivative could change signs at a critical value at it or at a discontinuity, which happens on either side of a vertical asymptote. Okay, so how do we find these intervals? So if we let f be a continuous function on a closed interval ab, to find the intervals on which f is increasing or decreasing, we do these 3 steps. First, we find the critical values of f, including discontinuities, in the open interval AB. 2, we create a number line chart using these critical numbers. 3, we choose x values in between the critical numbers to test the sign of f prime on your sign chart. Now, we've done sign charts in pre-calculus to help us graph functions or find intervals of where a function is positive or negative when we were solving polynomial inequalities and rational function inequalities. So this is very similar to that. Please note on the AP test that just having a sign chart is not a justification. You have to write a statement that says why you know exactly that there is a relative min or a relative max, or there is an interval of increasing or decreasing. So there's an example listed here. So we can say that, for instance, a function g is increasing on the interval -2 to 5 since g prime of x is greater than 0, is positive. So that specifically tells the AP reader that you understand exactly what the sign chart is providing you with. Okay, so let's start with an example. We're going to determine intervals on which this function is increasing or decreasing. So we have a polynomial function, and we have to justify our findings. So what we're going to do first is we're going to find the critical values. What that means is finding the zeros of the derivative. So we're going to take the derivative, and we're going to get 2x squared minus 2x minus 4. We're going to set that equal to 0. I'm going to factor out a 2. Then I'm going to factor the quadratic, x minus 2, x plus 1. So I have 2 critical numbers. I have one at 2 and one at -1. Okay, so here is what our sign chart is going to look like. So we're going to have this, and then we are going to mark these values. Here's -1. Here is 2. And then we're going to pick x's in between them. And what I'm going to do on top is I'm going to put the f prime's sign, whether it's positive or negative, and below I'm going to put f's direction. Okay, so I'm going to choose the following x values. I'm going to choose -2, because I already know I have a 0 here. I am going to choose 0 here and 3 here. Now, again, I don't need the actual signs, but what I do need to know is whether f is increasing or decreasing. So looking at the sign of the derivative will tell me whether the slope is positive or negative. So substituting -2 into the function, so I am going to have -2 minus 2, so that'll be a negative number, times a negative number. So I get a positive sign here. So that means the function is increasing. It's going up. Then when I put 0 in, I'm going to have a negative times a positive, which will give me a negative number. So that means now the function is decreasing. And then at 3, I'm going to have 1 times 4, so that's going to be a positive number. So my function is increasing again. And you can kind of see that we're sketching the curve. I'm kind of going ahead because we haven't talked about the relative mins or maxes, but you can see how, especially with this continuous function, that we are going to have a relative max at -1 and a relative min at -2. But this problem is just asking for the intervals. So what we can say is that f of x is increasing on -infinity to -1, and also from 2 to infinity, because f prime of x is greater than 0. And we can say that f of x is decreasing on -1 to 2 because f prime of x is less than 0, so it's negative. Okay. So when presented with a continuous function, knowing that the sign of the derivative changes at a point c, f of c, as well as knowing how the sign changes, will give us insight into the existence of extrema, as I was showing you in our sign chart here. So this is what is known as the first derivative test to find local extrema. So what we start with is the fact we have c as a critical number of the function f, and we're assuming that f is continuous on an open interval. So if f is differentiable on the interval except possibly at c, then f of c can be classified as one of the following things. So first off, if f prime of x changes from negative to positive at c, then f of c is a relative minimum. So what we have going on here is the following. So we have f prime of c is negative, here's my c, and then it changes signs to positive. That shows that we have a relative minimum. So if f prime of x changes signs from negative to positive, then we have a relative maximum. So from positive and negative, I'm sorry. So it was going up like this. Here's my c, and now it's going to start going down. So you can see we've kind of made a maximum there. And the third option is if f prime of c does not change signs at c, then f of c is neither a relative minimum nor a relative maximum. And we'll get into that more as we go. Okay, so we will explore how to find points of inflection in intervals where the function is concave up or down in the next lesson. But until then, this is the chart that we can use all of our symbols from for the correct behavior. So we can see for f of x, we have 4 options. It can look concave up, concave down. We can show it's increasing. We can show it is decreasing. And we can do the same thing for f prime. We can show it's increasing. We can show it's decreasing. We can show it's positive or negative. And then next section is on the second derivative test, and that's how we find our concavity. We can talk about whether the second derivative is positive or negative. Okay, so let's go into example 4. Just so you know, for now, for the first derivative test, we're really just confining ourselves to this little box of symbols that we used in the previous example. The concavity symbols and the increasing and decreasing for the first derivative will come into play with the second derivative test. Okay. Okay, example 4, given f of x equals x to the fourth minus 8x squared plus 1, we're supposed to first find the open intervals on which f of x is increasing and or decreasing and justify that answer. And then we're going to determine the x values of any local extrema of f of x and justify. Okay, so we are going to go through the same steps we used just to find the intervals. We're going to first find the derivative. So f prime of x is going to equal 4x to the third minus 16x. We're going to set that equal to 0. We are going to find our critical numbers. And the nice thing is we have a continuous function, so we don't have to worry about any, because this has a domain of all real numbers, any undefined values of the domain of the original function. So we get 0, we get -2, and we get 2. Next thing we're going to do is we're going to make a sign chart. Let me just move this up a little bit. And our sign chart, we have a lot on it this time. So here's our F direction. This is our F prime sign. Here's our X's. We have one at -2, 0, and 2. And what we know so far is that each of these are a 0 of the derivative. So it's neither positive nor negative. So picking some X values, here I'm going to use -3, -1, 1, and 3. How very symmetrical of us. Okay, so substituting -3 in our derivative, and I like to use the factored form because I think it's easier. Then I'm just looking at two terms, whether I multiply them together and they're positive, or I multiply them together and they're negative. So if I put a -3 in here, I'll have -12 times 5. So that's going to be a negative number. So my sign is going to be negative. So that means my function is going down. Then I'm going to substitute -1 in. So I have a negative times a negative, and I'll have a positive number. So that means that the function has changed directions and going up. Next, at 1, I'm going to have a positive times a negative because I'll have 1 minus 4. So that'll become negative, and that's going down again. And then at 3, I have a positive times a positive, so I get a positive. And so if we wanted to, we can see where our extrema are. We can see we have a minimum there, a maximum, and another minimum. Okay, so now we can answer part A. So part A says to find the open intervals on which f is increasing and or decreasing. So f is increasing on -2 to 0, and also from 2 to infinity. And our reasoning is, since f prime of x is greater than 0, then it's going to be decreasing from -infinity to -2, union 0 to 2, since f prime of x is less than 0. And now we can do part B. Part B wants our local extrema, and so we know the x values. So we know there is a local minimum at x equals -2, and the reason for that is since f prime of x changes from negative to positive. And actually we can group in here too that there's one here at x equals 2, because it's the same reason. And then we have a local maximum at x equals 0, since f prime of x changes sign from positive to negative. So there's our justification, and that's putting together finding our intervals and also finding our local extrema. So I'm going to finish our discussion in the third video with a series of examples. As always, if you have any questions, please ask in class tomorrow.